Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is Basic Electronics 1. This video lecture is entitled Thevenins Theorem. This is actually version 2 of Thevenins Theorem because after 215,000 combined hits on YouTube, I decided I need to redo this because that audio was terrible in my first version. So if you are trying to find the first version, it's probably not there anymore. This is the new second version. It's the same content, just better audio. Okay, so Thevenins theorem is an incredibly useful theorem for basic and advanced electronics. You'll find yourself using it all the time. And what Thevenins theorem does, it's basically a matter of perspective. And that's all I want to do right now is illustrate a trick of perspective on this particular network I've set up here. It's an 18 ohm resistor, a 6 ohm resistor, an 8 ohm resistor, and a 12 ohm resistor. And my question to you is, what's the resistance of this network? The answer is it depends. It depends where you're hooking it up. For example, if I was to take my multimeter and look from this side, it would be entirely different than if I had my multimeter hooked up from this side. Why? Okay, so let's sticking from this perspective here, think about this. What the multimeter is with its small sensing current, it's coming out here, splitting up in these two current paths. So what that is an 8 in parallel with a 6, 18, and 12 in series. Okay, so let's do the combinations for a series. 6, 18, and 12 in series is going to be a 36 ohm resistor in parallel with an 8. Basically, I've just compacted it down. Ultimately, a 36 and an 8 in parallel is one 7.4 ohm resistor. Okay, so that's from the right side. Let's take our ohm meter, put it like we originally had it. It's the same network, but the results are different. Okay, because that small sensing current coming out of our multimeter is going down the 18 this way and going around the loop in this fashion. So what is that? Well, it's the 6 and the 8 and the 12 all in series in parallel with the 18 now. So 6, 8, and 12 all in series, that's a 26 in parallel with an 18. 26 in parallel with 18 should give you a value of 10.64 ohms. Okay, so we came up with two totally different results. From this side, 7.4 ohms. The other side, 10.64 ohms. It's a matter of perspective, how you hook things up, which side of the thing you're on. Okay, so that's what Thevenins theorem is. You're going to be using perspective to do analysis of Thevenins theorem. What Thevenins theorem is, it's a really great simplification tool. And what that tool does is basically states any linear two-terminal network can be reduced to a voltage source in series with a resistance viewed from the perspective of RL. So I'm going to go ahead and write that out. Okay, there's the verbiage of what I just discussed. And the critical point is from the perspective of RL. What is RL? Well, RL is what's known as a load resistor, or something that's applied to this particular network of interest. I've just drawn a simple example right here of a 9-volt source with a 3 and 6 ohm resistor hooked up in such fashion with our RL. So from the perspective of RL, everything attached to it here could be replaced with a Thevenin equivalent, basically what's inside the box. So what's inside the box could be replaced with a voltage source with value ETH in series with a resistance with a value RTH. that behaves exactly like the thing in the box when RL is hooked up to it. So the question is why am I replacing something that behaves exactly like something else? Well, here's the answer. It's easier. For RL, a value of 10 ohms, solve this network. For RL, a value of 10 ohms, solve this network. For a value of 100 ohms, 100 ohms, 1,000 ohms, 1,000 ohms, on and on and on. You get the picture. This network here is substantially easier to solve than what's in the box, okay? Because all it is again, it's a voltage source in series with a resistance. It's very simple. You could do a quick voltage divider rule. To determine the voltage across our load resistor. We could do a quick summation of those two resistances to determine the total resistance, and then use our applied voltage, in this particular case, the Thevenins voltage, with our total resistance to determine the current through the load. It's awesome. It's super easy and simplifies our work. So the question is, how do we convert what's inside the box to the Thevenin equivalent? Well, there's a couple steps here. And here's our basic 1, 2, 3, 4 steps. Number one, we've got to mark our terminals. For our particular example right here, terminals have all already been kind of marked, A and B. Because what we're going to do is we're going to remove RL. Now step 3, find RTH, find the Thevenin equivalent resistance. How do we do it? We're going to use RL perspective. Again, so this is a trick of perspective. Where are we looking for? Which direction are we looking from when we're finding RTH? We are looking from this side, from the side of the load resistor. Okay, from the side of the load resistor, what is that resistance it sees? Well, there's a problem. There's a source in the way. We have to remove a source. We have to remove all our sources when we do this. Okay, so what's our rule for removing sources? Voltage sources, we short them. Current sources, we open them. So our 9-volt source, short it. What do we see from the perspective of RL? Very simply, it's a 3 in parallel with a 6. So RTH is equal to 3 in parallel with a 6. Should be equivalent to a 2 ohm resistor. We're already halfway done with the problem. 2 ohm resistor. Okay? Now, step 4. Find ETH. Means we got to put our source back in. 9 volts in that particular orientation. And it says, find the open circuit voltage at the terminals of interest. So now we've shifted perspectives. We've got to figure out from this perspective, from the perspective of the source, what is the voltage on terminals across terminals A and B. So there's a number of ways to do it. We could figure out, okay, it's a 9-volt source, seeing 3 and 6 in series. Okay, so it's a trick of perspective. From the perspective of the source, it sees a 3 in series with a 6. We previously saw from the RL perspective, it saw a 3 in parallel with 6. So again, it's a trick of perspective. Looking from the source side, we see 3 in series with a 6, which is a 9 ohm resistance. We would expect 1 amp of current to flow. When 1 amp of current is flowing through a 6 ohm resistor, because it's in series, we should get a plus to minus 6 volt drop. Another way to do this, because it's a very simple circuit, just do a voltage divider rule. Applied voltage, 9 volts, times total resistance, resistance of interest divided by total resistance times total applied voltage. So 6/9 of 9, obviously 6 volts, you get the same answer. Okay, so you're just using current to solve for the voltage or use a voltage divider rule. Either way, you get the answer of 6 volts. There you go. Our network can be simplified with a Thevenin equivalent resistance of 2 ohms in series with a Thevenin equivalent voltage of 6 volts. Now, for those of you that are not convinced with the advantages of solving circuits using Thevenin's theorem, I hereby challenge you to a race. What I want you to do is figure out what the current is through a load resistor of 100 ohms using that circuit, while I solve it using this circuit. Okay? So, go ahead and get your pencils ready. Go. So my I source is equal to my total applied voltage divided by RT. So it's 6 volts, RTH, ETH, 6 volts. It's a 2 in series with 100. So 6 divided by 102, 58 milliamps. What is that current through the load resistor? It's still 58 milliamps because it's a series circuit. What's my voltage across my load resistor? Well, it's 100 ohms times 58 milliamps, 5.8 volts. Okay, so check it out. I'm finished. I've already figured out what my voltage across my load resistor is and the current through my load resistor because it's a simple series network. I could have just as easily solved using a voltage divider rule of 100 divided by 102 times 6. You'd still get the same result of 5.8 volts. Now, compare and contrast the calculations that I just did. Here's one calculation, 2 calculations. I'm going to put the answers over here. 58 milliamps, 5.8 volts. With the rigmarole that you're going to have to go through using the above circuit, your original circuit. Okay, so it's our 9 volts. We're going to add 100 ohm resistance in this fashion. So what we're going to do is we're going to go ahead and simplify the circuit. It's a 6 in parallel with a 100 in series with a 3, 9 volt. What is the calculation that we're going to have to do there? That's one calculation. 5.66 ohms. 2 calculations. 8.66 ohms. Source current, figure it out, 1.039 amps. 3 calculations. Expand that back out to our original expand that back out to our 6 and 100. We're going to have to do a current divider rule because I know 1.039 amps enters. Here, I'm going to clean that up here. I know 1.039 amps is entering that node and it's splitting between the 6 and 100. Which way does it go? Well, 100. 6 plus 100. 1.039 amps. How much goes through the, whoops, I messed that one up there. Should give me 58 milliamps. Okay, what was that? 6 steps right there that I had to go through to get that, which I got that in 1 step. Okay, now I'm still not done. I've got to figure out what the voltage is across my 100 ohm resistor. Well, 58 milliamperes through 100 ohm resistor should give me 5.8 8 volts using Ohm's law. So it was what, 6 or 7 calculations that I had to go through, and some tedious collapsing and expanding of that particular circuit. And now here's the catch. Do that for another resistor. Do it for a 1.2K resistor for that same circuit. You would have to go through all 7 or 8 steps again. Here it is. 1, 2. Bang, I'm done. Okay? Now do it for a 2K resistor. Another 7 or 8 steps. 1, 2, done. Okay? That's what's the advantages of Thevenins theorem. It basically simplifies any two-terminal network with a voltage source in series with a resistance, and it simplifies your calculations. And the trick of doing this, the whole trick, it's not like it's really any crazy mathematics or electronics theories that you have to realize. It's just a trick of perspective. Where am I looking to from, and where am I looking to? Okay, let's try another couple examples here. Okay, so here's our second example. We've got a 12 volt source, a 30 ohm resistor, 30 ohm resistor, a 45 ohm resistor, when we've got a RL hooked up in the following fashion. Okay, so we're going to mark our terminals A and B. Step 2, remove our load resistance from the perspective of where the load resistor used to be. What is the Thevenin equivalent resistance? Well, got to go ahead and remove our source first. It's a voltage source. What are we going to replace it with? A short. Okay? How does this look from the perspective of the load resistor? Again, perspective. Well, it looks to me like it's a 30 in parallel with a 30, which we all know is a 15 in series with a 45. That should be pretty simple. It's a 60 ohm resistance. Halfway through the problem already. 60 ohms is my RTH. Let's go ahead and solve ETH. Go ahead, put our source back in. It was 12 volts. Now here is something tricky. It is open circuit voltage. Open being the operative word. Open meaning no current flows in this direction. What does this mean? There is no current flowing through the 45. If, according to Ohm's law, voltage is equal to current times resistance, and current is 0, our voltage drop across our 45 ohm resistor is 0. Okay? Check it out. That's not even there. Forget about it. Okay? Simplifies it again. Okay, so now there is 2 ways to solve for what that voltage drop is. You can do a simple VDR. You don't even really need to calculate this one because they're 2 identical resistors. What is that? 6 volts. VAB is equal to 6 volts. So our Thevenin equivalent voltage, 6 volts. Our final answer will look something like this. If you want to go about this in some more complicated fashions, let's bring it out here. So 30 plus 30 times our applied voltage, 12 volts. That's our voltage divider rule. You're still going to get 6 volts. You could also 12 volts divided by 60. You term your source current, IS times 30, still is going to give you 6 volts. There's a number of ways to depilate that feline. Skin the cat. Okay, so we've simplified that network into a single voltage source in series with a single resistance. Substantially easier, again, to perform calculations on that than this guy up here for various combinations of load resistance. Go ahead and try it. Put in a 100 ohm resistor. Put in a 3K resistor. Count how long and how many steps it takes you to solve for IL, VL, for the heck of it, PL, using that above circuit. Now, do the exact same thing for a 100 ohm resistor and a 3K ohm resistor, IL, VL, and PL. See how many steps it takes. 2 to 3 each time. Bang, bang, bang. You're done. Use the Thevenin equivalent. Let's do one more example. Okay, so here's another example. It looks like we've got a current source, a 40 ohm resistor, a 20 ohm resistor, and an RL of unknown quantity hooked up in the following fashion. Let's say we've got a dozen different types of RL, and we need to go ahead and calculate IL, VL, PL for those dozen different types of RL. So before you start doing the calculations of those dozen different resistors, those are dozen different load resistors for that particular circuit, my advice to you is stop. Don't do it. Take a breather, do the Thevenin's equivalent of the circuit, and then calculate the IL, VL, and PL for those dozen different resistors. Okay? So stop, don't do it. Let's do the Thevenins. Mark terminals. Bang, they're already marked. Remove RL. That's easy. A, B. Calculate RTH. Oh, we've got a source in there. How do we remove it? Do we put a short in there? No, it's a current source. We put an open in there. Okay? So this is a neat thing here. What do we see now? From the perspective of the load resistor, what do we see is a 20 in series with a 40. Okay? No big stretch of the imagination there. RTH should be 60 ohms. Halfway there already. Okay? Now, let's go ahead and put on our source back again here. Here's our 2 amp. And we're going to go ahead and figure out what is the open circuit voltage. Okay? Again, from the perspective of the source, what is the resistance it sees? Well, check out this huge open gap there. Is there any possible way for Johnny Electron at terminal A to get to terminal B? Negative. There is no path. No current flows through that 20 ohm resistor. Ignore it. Therefore, all 2 amps goes through 40 ohm resistor. Voltage, I times R, 40 times 2, 80 volts. There is our Thevenin equivalent resistance for those dozen different combinations of RL that you wanted to use it for. Still don't believe me? Again, I challenge you to a rematch of the race. You got to use this circuit. Whoops. You got to use our original circuit. 20 ohms. RL. And let's say RL, it's 100 ohms. 100 ohms. Okay, let's figure out what the IL, VL for 100 ohm resistor. Get ready, get set, go. So here I am, just kind of waiting for you to even start simplifying your circuit. I'm going to give you a little head start, and here I'm going to go ahead. My source current is equal to my applied voltage divided by my total resistance. What's my total resistance? 80 volts applied voltage, 60 plus 100, 500 milliamps. I bet you're still doing parallel calculations. Voltage across my load, 500 milliamps, times my resistor of 100, 50 volts. Not bad. One step, two-step. Okay? Try to do that for 100, 1,000, 3K, 4K. You get the picture. Doing it the Thevenins equivalent way is substantially faster. So again, what are you doing? You're taking that super complicated network, simplifying its entire behavior down to a single voltage source in series with a resistance, and the trick on doing it is perspective. Okay? One thing I like to highlight here is, again, that trick of perspective. From RTH, when we were finding RTH, when we removed our current source, 40 and 20 were in series. From the perspective of ETH, 20 was now open, and we calculated all voltage across the 40 ohm resistor. So again, it's changing the state of the circuit depending on your point of view. And the key thing is here is these calculations I performed for a 100 ohm load resistor. Don't believe me? Do those same calculations. Take the time. Do it. I guarantee you're going to get 500 milliamperes load current, 50 volts across that load resistor. Okay, this concludes this portion of the lecture for Thevenins theorem. The next follow-on lecture on this is we're going to deal with this bad boy right here, which is, if you look at it, it's a two-source network. So again, this lecture was just dealing with single-source Thevenins theorem, and so next lecture is going to be two-source Thevenins theorem and the maximum power transfer theorem.